In this lesson, we will continue the discussion of the contains operation on a list and how we can improve the speed of finding our element. So, in the last lesson, we saw that the contains operation is an O(n) operation, which means that if we want to verify all the words in a file, we would come up with an O(n) squared operation. And this is quite expensive, as we learned already, and we saw in the labs that this is very slow. So one solution to this problem, you might think a good way for you to see a possible solution to this problem, which we will actually implement, is to think about a dictionary, but the paper dictionary, the book version, that you probably don't use anymore, but I'm 43 years old, so I still remember using them at school. And one of the properties, the most important property of a dictionary that allows us to find a word much faster is that it's sorted. The fact that it's sorted allows us to not have to search through all the dictionary, which was the problem with our contains. To know if a word is there or not, we have to scan through the whole list because the list is not ordered. So to visualize this, let's look at this representation. Here I have letter A, here letter Z or Z, and here let's say I have letter M. And if I want to search for the word hello, and I open the dictionary in the middle and I see letter M, I'm 100% sure that I can ignore all this part. Right? Because for sure it's not there. And then I have to search on this side. And if I cut here in the middle again, and here it's letter I, for example, I know that I have to search on this side, and I can ignore this part here, right? So in each step, we are ignoring half of what we need to check. So the name for this is a binary search. That's the technical term for this type of search. And as you can see, this is much more effective because at each iteration, we are ignoring the half of our input. So the function that mathematically represents this type of growth is the logarithmic function. So this would be log of n, which would be represented like this, which means that it grows very fast at the beginning, but then it goes close to a constant. So here, even if you have millions and millions of elements, already on the first iteration, you ignore half of your input. So this is the power of having our function, our data sorted. But now you might wonder, because we are using a linked list, we have an issue. Because if our lists in our linked list like this, the problem here is that on a list, we only have a reference to the first element. So if we cannot directly access the middle element, then there's no way that we can do a binary search. So how can we solve this problem? I will let you think for a bit. Please pause the video and think how this can be solved, and unpause the video once you think about a solution. So the solution to this problem is to not use a linked list. So with a linked list, we cannot do this type of binary search because, of course, we don't have access to the middle element, and this would not allow us to perform this binary search. So from now on, we will study another data structure called a dynamic array that would allow us to perform this binary search. So for now, we will do a break on the study of linked lists. We will start with the new data structure, and we will learn how to implement the same operations that we did on the list, but using a dynamic array. See you in the next one.